Right, week 120. What is up, everyone? Nice to be back after a couple weeks of not being live. Yeah, I had 3 weeks of pre-recorded streams while I was away, but now we're back with stream 120 of working on my operating system. So I'm just gonna post in the Discord. Yeah, I'll need a bit of a moment just to reset a little bit and see what I want to do today. But I have some ideas, but I'll just start off by, I think, recapping the current state of progress a little bit. I was just running the kernel after a couple weeks of having not touched this, and we are page faulting. It was something to do with this work on task stacks that we were doing previously. Let me update my title. It's week 120. Hello to everyone joining the chat right now. As usual, put the test 0 in the chat to test if the chat bot is alive today. Sup, Temple? Here's to learning. That's right. That is right. All right, seems like the chat bot is actually asleep. Maybe it'll wake up soon, hopefully. Yeah, let's talk a little bit about what we want to do today. So let me recap a little bit. What is going on with the OS lately? And so in the last couple of weeks of pre-recorded streams and working on this, I was working on some smart pointers. That was week 115, maybe like these 17 and 18, I think. We were doing some smart pointer stuff, and let me just close everything out. So the smart pointer stuff was related to the task stacks. And so the task needs a stack to run on. And okay, chatbot woke up. It seems like that's cool. So yeah, all tasks need a stack to run on. And we need to allocate a stack when we create a new task. And then when a task exits, we need to free the stack. So this is a very natural application of a smart pointer. And I'm pretty happy with how things are looking. And so the code in the scheduler that's creating, what's up, OKG? Bemi Joshua. What's up, man? Thank you. So yeah, here's what the code looks like. And so we're creating a new task. And before we construct it and add it to the linked list, we allocate a stack for it. And then we create the unique pointer and pass that into the task. And so then the task now has this pointer that is the owner of the stack. And the benefit we get is that now when the task gets destroyed, when the object is destroyed, the unique pointer will automatically free the stack. Yo, what's up? What is up, everyone? What's up, Kumar? What's up, Shub Devs? What's up, Aryan? And VA80. Nice to see everyone. Test 3. Let's go with the test 4, just to make sure. Kumar, you can check out my resources page if you like. It is a little bit ad hoc, but it's a collection of links and things I've collected. Right. So I was doing some smart pointer stuff in the last couple weeks in the pre-recorded streams. So that was one topic. And I'm a little bit out of practice with my stream setup. Okay. What's up, Melchi? Okay. So just to recap, so smart pointers, topic number 1. Oh, Shub makes content also. Nice, man. I'll check that out later. Thank you. Topic number 2, stacks. And so the situation was very prototypey when my tasks, so they have stacks, but the stack is not allocated in the virtual address space, really. It's running, the stack is located in this special region of the virtual address space called the fizz map, which is a special region, and it exists as kind of a convenience mechanism, but it's not really suitable to use the fizz map for a lot of production use because it's this massive read-write region of all of physical memory. And so you lose many, if not all, of the benefits of virtual memory when you start relying on the fizz map too much. And I was using the fizz map extensively for this. So the goal is to properly allocate the task stacks somewhere in the kernel virtual address space. And that's what I was trying to do in week 119, maybe even week 100. Looks like not really. Like I think week 119 is when I started to work on that. And then we were doing that in week 119 and 116, which confusingly 116 happened after 119 due to the way I pre-recorded things. And that was very interesting. There were a lot of problems with my effort to try to do the stacks correctly. Mainly, the main problem was I was storing the stacks all in this pool. It's like this pool data structure from ETL, which is this library I'm using. And that seemed really nice at first. I can allocate things from the pool and free them back to the pool. The problem is with the guard page. So with my stacks, there is the idea is to have a page of unmapped memory at the bottom of the stack to catch stack overflows and force a fault to happen. And that conflicted with the pool, which is not designed to be used that way, where suddenly the start of the entry becomes unmapped. And that was causing crashes. So we were seeing, I guess we were seeing page faults, I think. Yeah, I think we were seeing page faults when ETL would crash when it would manage the pool, because ETL requires that the memory stay writable, and it actively uses that space for empty objects. So that was a big problem, and it's an unsolved problem. I think that was the last point that we stopped with last time. Yeah, I think we stopped there last time. And I have some ideas for what to do about that. And it could make sense to keep going with that. I think I'm feeling a little bit cold, like not physically cold, but like I'm a bit out of practice. And so I'm a little bit intimidated to jump right back into that kind of complex topic, but maybe we can find a way to ease back into it. Never regret subscribing. Oh man, what a compliment. Thank you, LG. If I'm saying your name right. Ariane, you guys were talking about user space stack and kernel stack. It isn't only kernel required, it will do the context switches. Let me see if I don't know if I understand this question you guys were talking about. Ariane, were you talking about in the Discord? We were talking about some of the stuff like this in the Discord recently. I mean, only kernel required, it will do the context switches. So if I'm reading your question right, so I think I'm agreeing with you. So from my perspective, the scheduler only switches between tasks that are running in the kernel. And so if a user space task needs to get scheduled out for some reason, that's going to happen in one of two ways. The first way is it's going to be a timer interrupt that's going to forcibly take the user space task off of the CPU. And the timer interrupt is going to trigger an interrupt, which is going to enter kernel space. And that's the state where we can freeze the task and then resume it later. So that will be in kernel mode. The second option for when a user space task is going to pause or suspend or sleep or whatever is if it explicitly makes a system call that is going to involve blocking it, like sleep, like waiting on a mutex, like waiting on a file IO or whatever. In that case, it's going to make a system call that calls into kernel mode. And again, we're going to be in kernel mode, and so we can freeze the context there in kernel mode. And so the idea is that everything, any kind of situation where a running thread gets suspended is going to be in kernel mode. Then the scheduler, when it's switching between things, it can rely on that fact and just from its perspective, it doesn't actually know anything about user space. It's just seeing these kernel threads and it's switching between them. So anyway, that was my understanding. What's up, Temple? Is it Linux compatible? No, we're not doing any Linux compatibility. Definitely not right now. Probably not ever for the future, I think. Because that just does not sound fun to me. Yeah. Okay, so anyway, so basically let me just map out what I'm saying. And so I've just been recapping, and so smart pointers, was done. Improve how we map task stacks. That's in progress. And then I'll give a bit of a shout out, and I'll mention another piece of work that came up, and we could do it or it could be for later. I got a really, really good comment on Instagram from Jakub, who was critiquing my scheduler code. And Jakub made actually a really good point that I'm pretty convinced by. And so currently I have this task struct. It's like this object representing a task that's running on the system. And inside the task, I store a register state, which is what it sounds like. It's just a storage area for all the registers on the machine. And I'm storing that inside the task object, directly inside the task object. And this made sense to me just intuitively when I was sort of sketching out this structure. It seemed like a very natural thing to do, to represent it this way. But as I learned from Jakub, there are some problems that are caused by this, and there are alternative designs that simplify things. And so to be very specific, I will explain after a 20-second break, so feel free to join me for a 20-second to stand up and stretch. So what's up, W. Ronan? So I guess not to spend like an incredible amount of time on this, but the problem is if we look at the yield the task yield API, which tasks can call to yield and suspend themselves, what it looks like is I call this routine called assembly asm sched yield preserve task, and I pass in a pointer to the register state. And actually that's not the problem. The problem is with restore. And so sched.s. Problem is with the restore. So like, well, let me just actually find, and so restore is called here in switch to task. We have a new task that we want to switch into, and the most important part here is just seeing how this gets called. We're calling into this routine or passing in a pointer to the register state that we want to switch into. And because we're past a pointer to this register state, it's a little bit fiddly. And so we're using all these offsets from RDI, which receives that pointer. We're sort of spilling a few things onto the stack in order to restore them, specifically the flags. And then also ultimately to do the jump back into the task we spill the PC onto the stack and then do a return. And then there's this ordering issue where RDI, which is holding the pointer to this thing, needs to be restored last. And so that's what this routine looks like as a consequence of doing it this way, where we keep it in a pointer inside the task object. And so there's just a bit of this complexity with the ordering and whatnot. So what's up Galred? And so what what Jakub is saying, saving into the struct seems kind of pointless. You already have a perfectly valid per thread kernel stack. You can just push the old context, switch the stacks, pop the new one, and ret IP is automatically saved and restored. That way you won't have to do that stuff with pushing onto the new stack as you can clobber. I give you a B for effort, for Beffort. So this is saying, why would you do it this way when actually you could push the context onto the stack directly? And then that is actually going to simplify this assembly quite a bit. It's going to mean that there's no need for the RDI. It's going to be the stack pointer. And then all of these moves are just going to be pop, 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 pop. We're just going to pop all these things off the stack. We just do a pop FQ because, you know, our flags is saved and restored via the stack, and so we don't need to do this weird push thing. We can just keep popping everything, including the PC, to do the final return. And so it pretty much reduces the restore routine to just a sequence of pops and then a return. Yo, what is up, NSG? SC man, I am just discussing exactly the thing we were talking about in Discord, which is this this comment I got on Instagram. So honestly, yeah, I think I sort of want to just jump into trying this. Maybe especially if you're here. I think that's sort of I don't know, a nice little warm-up thing for today. We can play around with it. Yo, so what I need to do first though is like, there was so much random junk here. This is all like my experimentation to try to do that unmap guard page thing. Yeah. All right, I need to figure out what I All right, for the purpose of just moving forward, I think here's what I will do. I'm just going to commit this whip temp broken state ETL crashing question mark. All right, no doxing, please. What a rude question. All right, let's give me 1 second to adjust something in the chat bot. Sorry, 1 second. All right. Yeah, I just fixed something in the chat bot. Cool. Yeah, let's okay, let me just, so what I'm gonna do, I'm gonna just make a new branch back when things were a little bit less broken, so we can work on this nice little warm-up activity. And I think I'll make it right here. I do not want to, I want to do a reg state on stack. We'll call it that. Let's just the builds. Let's just see what state we're in right now. Okay. I think this was okay. This was like still in the middle of sorry, clearly. What editor? I'm using VS Code. But this is the problem. Yeah, I randomly was making the idle task exit for some reason. Let me just comment this out. Okay. Okay, good. So idle task. And so okay, just to get back to a state where we can get things testing, I want to get us back to something like this. What's up, Liam? I'll give a recap before I'm just preparing myself, but yeah, we're just working on some context switching stuff. Also, what's up, Sai Kumar? Okay, so this is sort of reverting things back to a simple state where we actually have a system that is running kind of recursively, I think. So let me just I just want to get it back. Give me 1 second. We're almost there. Dang, this is crazy. Yeah. Almost there. So I just need to, I'm not quite sure why the unmap is failing. I'm just going to comment that out for now. Okay. So this looks pretty good. Give me 1 second, it's like a bit warm over here. All right. So this is what the OS looks like when it's like running some tasks. And it's kind of impossible to read because there's a lot of print output. Maybe I will get rid of some of that. We'll get rid of some of these prints, and then in the In the smart pointer, I'll also get rid of this print. Okay, so yeah, this is our OS so far. And what it's doing is it's demonstrating taking tasks, running some code in a task. The task spawns another task, and then the tasks exit. I'm gonna check the chat. Temple, I'm using Limini bootloader, which is a good bootloader, and it has a lot of fans, and I'm one of them. It's knowledgeable with Sana. Sorry for existing, bro. It's all good. You're good. You're good. So just to be very clear, we have our task test. It's a task called test 0, and when the kernel starts up, it creates a single task on the system called test 0. And so test 0, it gets the current thread ID. It prints hello. It does a few iterations where it is printing out things, and every 5th iteration it yields itself to something else on the system. And then after that, after it finishes, it creates a new task, and then exits itself. And I guess really this makes the most sense when we have a couple of these things. And so now we have a couple tasks that are each running this function, and they're going to switch between each other when we hit the task yield. And so it's not really going to look different, but yeah, I mean, it looks exactly the same, but that's what it looks like when the tasks are running and context switching is working. And I think I did have some of these kind of sleep loops in there to slow things down so we can even see things a little bit better, but it's still kind of fast. I think one thing I'll do to make this a little bit more understandable is I won't create a new task. And so that means we're going to have a finite end after the 3 tasks run and they all complete, the system comes to a halt, which is what we want. And so you can see more clearly the hello from task 1. And so actually they each do a yield on their very first loop because of the way I wrote the modulus. And then task 1 runs a couple times, runs 5 times, then it switches to task 2, which runs 5 times. Then we switch to task 3, which runs 5 times. Then we switch back to task 1. And so the point of all this is just to show that it is doing scheduling. It's switching between the tasks. And it's not crashing. The kernel's not crashing when it switches between tasks, and it's able to seamlessly do this and also preserve the state of the task. You can see that the number, when it switches back to a task, it picks up from where it left off last time. And the reason I set this up right now is because if we want to work on this code change that was suggested by Jakub, we want to have a stable environment to run after we do the change to make sure it works. So let's do it. Let's do it. Okay. So I'll just do a little commit whip get basic tasks running again. Okay. So what do we want to do? Let's plan it out a little bit. So in general, we want to remove the register state from here actually. So the task is no longer going to have a register state. Maybe it'll be helpful to have an illustration. So as usual, we've got some memory, and we have our stack for a task. And then let's say over here, I mean, this is also in memory, but just to make it clearer, we have the task object. I mean, realistically, it's also in memory somewhere, but I'll just put it to the side over here. And then here is our stack. Currently, there is this block inside the task. That's the register state. It's inside the task. Let's say we have a stack frame of some code that's running on the task. The idea, and then let's say a yield happens right at this point. And so we're running some code, then the task calls yield. Currently, some assembly code takes the contents of the CPU registers and populates them all over here and saves them for later when we want to resume this task. Like I mentioned a bit earlier in the stream, there are some problems with doing it this way, and an alternative design is to actually push it right here. Alternate location for register state. And then with this new design, we would no longer store the register state over here. What we would actually store is a pointer to bottom of stack / register state. And so in the task, we would store a pointer right here. So the pointer to this thing. And doing it this way is going to allow us to simplify the assembly routine for restoring a task. So that's the idea. And let's start sketching it out. And so I'm just going to comment it out for now, but I'll replace okay, well, so I think I need to think this through a little bit actually. So register, because this is kind of interesting, because actually I am actively using the fact that a task stores a register state in order to initialize it properly. So that's one thing I didn't consider. And so so problem. The instruct register state is actively used right now to set the initial state of the task. So that's kind of interesting. So doing it this way makes it really easy to initialize the stack pointer. And also, what about the PC? Oh, time for another 20-second break. Be right back. What about the PC? Wait, let me. So this goes back to over here, create task. Also, this is relevant. This is relevant. So we can see that. So we said a couple of things here actually, which is kind of interesting. What's up, ZRO? The 20-second break is called timeout. It's like this Mac app. And we got this big brain comment that I just do not understand in the chat. What's up, Leo? What's up, Useless? It's going good, man. Nice to see you. Nice to see you. It's been a while. Yeah, working on refining the context switching. Let me try to clarify this. And so, number one, store the context inside the task struct. 2, store the context on the stack. Store a pointer in the task struct. And this is how I'm doing it currently. I call it the register context. And here's the alternate method. And let's talk about pros and cons. Pros and cons. So the pro of this is it somewhat intuitive object modeling. The con is like this is a bit more ad hoc data storage to store it on the stack like that. The con is that it somewhat complicates the assembly to restore the task, and then the equivalent is here somewhat simplifies the assembly to restore the task. Yep, you can still keep the context structure as a pointer and point to the end of the stack. Exactly, yeah, that's exactly what I'm trying to do. Yep. And so the little roadblock here is just this part. How do I replicate this? I think, so what I need to do, let me just, tasks.hpp, right. But exactly, yeah, that's what I'm trying to, alternate location. Yeah, so this is a stack frame, and then our register state goes here. And the tricky part is, C or C++. I mean, yeah, I think if you're released, I think C++ only makes sense if you kind of know C++ already. But if you don't really know either, I think probably C makes sense to start out with. It is simpler. Okay, what's the first thing we're gonna do? The first thing I'm gonna do, yeah, frankly, I would even maybe skip C++. I would just go straight to Rust. Really, I think really the main reason to use C++ is if you already know it and are most comfortable with it, like I am. Okay, so roughly this is going to look something like this. We're going to store a pointer to a register state in this thing, And then over here, I need to pass in a couple of things. So I need to pass in a couple. I'll pass it maybe like right here. And so for T, this is like kind of bad, but I'm just going to do it like this for now. I'm just going to pass these as arguments. And so I'm going to go over here. This is how I'm just going to save a stash of that just so I can reference it. But then the idea is right. This. Rip. So instead of constructing the register state and then customizing the RDI and the rip and then passing that object, like constructing that object here, we're only passing the specific values, like the RDI and rip. And yeah, and then, so now, so register state doesn't exist anymore. And this is no longer a thing. And what we need to do is I think we need to prepare the stack, basically. And so I'm going to do this in sort of a bad way. For the moment, I'm going to snooze the inline suggestions for 5 minutes while I try to do this. And so I'm going to do this in the worst way possible, and then we can refine it later. The worst way possible to do this, I'm going to have a task register. Actually, you know what? This code is pretty much what I want, actually. So I rip. Okay, so state. And so oh, actually, you know what? I see. So technically, I didn't need to do this. I see. So I could actually, just for the purposes of prototyping, I can actually revert this whole thing back. So it's a little bit inefficient because we're copying the task struct, but actually, so we just have this register state, and then we just need to write it into memory. And this is very interesting. So I'm going to make this thing not const anymore. It also doesn't need this thing because it's no longer being stored. We're mutating this, and then, okay, then the idea is we just need to write it into memory at, right into memory. And the way we do this is I need to get, so what does the stack look like again? So we get the stack top, right? We compute -1 pointer. register state equals stack pointer task entry minus size of task register state. Stack, right? Just to visualize it. And so this is the very top of our stack, right? The very top of our stack looks like this. We're going to rectangle. Yeah. So we have our landing pad address basically. The stack pointer is going to be initialized to start right here. And then we will need to kind of create our initial register state, and then the task struct pointer to register state is going to point right here. So that's the idea. And so I'm going to take, so the stack pointer on task entry points to right here. And so I need to subtract the size of the register state to get this pointer. And then I can do like something kind of crazy. So, and this is going to be a pointer to task register state and task, what's it called? Register state. So obviously still prototyping, but I think that's the rough idea. And then of course the very last thing we need to do is set p register. Oh, am I aliasing it? I am. That kind of sucks. Called MP register state. Exactly. Maybe NSG can give me the code review on this. But I think that's mostly right. What's up, Balaloop? Yeah, so we're preparing this register state. We compute the location and memory where we need to write it to. And then we write it there. Subsoup. HPP is a header file for C++ in the way that I'm naming it. People have different opinions about how to name things in C++, but I name it with HPP. Guys locked in, not gonna lie. That's true. So yeah, that's the idea. What's up, Ari Hunt? Watching this as a Python developer in first year of college. Dude, I remember being there. Dude, yeah, when I was a first year in college, I didn't know anything. I knew like a little bit of HTML. I knew like some HTML. I literally didn't really know Python. I didn't know anything. If you know Python and you're in your first year of college, you are farther than I was. Okay. So that is sort of what I'm thinking there. What we also need to do is we need to take a look at this thing though. A couple things are not going to work about this. Okay, a couple things are not going to work about this. So I think a few changes we need to make. So first change is rip needs to actually go actually, wait, maybe this is not so wrong. So the way this is going to work is that basically we have the structure in memory, and man, that's kind of annoying. Miro got kind of annoying with it pops up this menu all the time. So at the top is basically the PC. And under normal situations, the compiler is going to push the PC. So that needs to be at the end of the structure. Followed by basically all the rest of the registers go here. And so actually, and then the thing is, so I'm going to flip a few things around. So our flags is going to go here. We no longer need to store RIP, we no longer need to store RSP, and then RIP is going to go at the very end. So the point is I'm trying to make this struct layout match what is going to be in memory here. What's up, Thanosor? What distro do I use? I use Mac OS. Word. All right. So I think I've made my struct layout match the memory layout pretty well. So actually, let me see actually. So this is interesting. We no longer, yeah, I think we just don't need this anymore. Yo, what's up everyone? What's up, new assembler? What kind of OS are you making? I'm making a very small OS. I'm making an OS in C++, and it seems to be leaning more towards the real-time OS design space so far. We got 33 people in the chat. That's cool. So it's a good chat day. Got 33 people. Any good books for assembly? That's a good question. I think for assembly, I would recommend Pone College over anything, probably. I think you don't really learn assembly by reading a book. You learn assembly by reading some binaries, by disassembling binaries and reading them, and then doing some reverse engineering, and then also learning to write some exploits, and that's how you learn assembly, in my view. All right, so the task gets its stack, and it starts populating the stack a little bit. It sets up the landing pad, and then it sets up the register state on the stack. Got something to do today, maybe tomorrow I'll watch the stream. Yeah, it'll be up. All the streams get preserved. How long it took you to reach this level of C++? I have been doing C++ since 2019, let's say. So it's been 7 years, I guess. I think this works. I mean, we will see, but so far, compute the pointer down, and then we cast it to a pointer to task register state, and then we write that thing in there. So Then the last thing we do is we set the M register state. I mean, we can be kind of more verbose with the naming. It's really the register state on stack. It's really. So Fatih, is this real? 120 weeks? You bet, for sure it's real. Yeah, you can find every single video on my channel. Can you actually? Let's just confirm that. Yeah, so most recently 19, 18, 17. Some of them are on the videos, most of them are on the live. And then 16, 15, 14. All the way back to 2 years ago. So yeah. All right, so we got a register state on the stack. And yeah, I think what we got to look out for now is the scheduler. So let's actually take a look for where are there references to register state. And so a lot of this is no longer going to compile because we've gotten rid of this. We'll use this as C++ or Rust. That's a good question. I've got the 20-second break timer. All right, I'll be right back in 20 seconds. So I think overall, I would recommend Rust. If you are just starting out, if you are learning today, if you don't specifically want to work on C++ code bases, I think I would recommend Rust. But I think C++ is not as bad of a language as the discourse makes it out to be. And I think if you have ambitions of working for companies or industries that use C++, I think you should learn C++ then. It's a wet boon. Should I go for embedded systems or full stack as a fresher? Man, it's whatever, I would say just whatever you're most interested in. Yeah, it's not really something I can answer for you. It's not. What would you do if I said just do embedded systems? Like, would you just do it just because I said so? That's a pretty major thing for you, right? You need to make that call for yourself, and it's not as simple as me just making that call for you. All right, so this is interesting. Yeah, so a bunch of things are going to change here, actually. As a systems engineer, Rust or C++? Yeah, I mean, probably Rust. Like I said, it depends on if you have certain ambitions to work specifically for C++ companies, but otherwise, I would just go with Rust. What's a Vishnu? No network stack, just no network stack yet. Okay, let's talk about the simple case first. And so in the simple case, also one thing that's interesting is now we want to assert that we have this actually. Yep. Yeah, what's up, Omar? What scheduling algorithm? We're using the round robin scheduler, very basic, because that's not really the most important thing to me right now. Okay, now let's talk about how to implement the restore routine. This is the juicy part, actually. Well, actually, it's both of these. Let's see. So maybe I'll even just note some. So what are the parts of the code we need to adapt? We need to ask task struct. We need to adapt the SM for save, SM for restore, any other parts of the scheduler, like switch to task and task yield probably. These are the different components we need to make sure to update. And so we've already done the task struct. Now let's talk about some of these other things. So I guess let's do the yield first. I think the yield is going to be the easier part. And so what's up with the yield? And so previously with yield, we pass in a pointer to a register state. Where did you learn all this? I've learned it from a bunch of places. I mean, this OS stuff, I learned it from this free MIT course, which I actually streamed it for the first year of my streaming. No, oh, wait, T. I might really, the translate function is on or something like that. Do I recommend Practical Vim? I think that's a book, I think I've heard good things about it, but I don't know too much about it, but I've heard it's a good one, yeah. So I'm only doing kernel mode for right now. There's no user mode. So there's no Linux. It's no Linux kernel, it's a custom kernel. For starting building an OS, I think you should be very comfortable with C. You should be very comfortable with C programming, with pointers, with structures, with memory allocation, freeing, allocating memory, stuff like this. You should also know some OS concepts and play around with user space programming with that. You don't need C++ particularly. Okay, let me lock in a little bit here. So task yield. And so the idea is we are no longer going to pass an argument to this function. A task is going to enter here. It's going to call into this thing, which is going to push things on the stack. And so that's the idea. So right, so let's first look at this. Can you suggest some projects to master a language like Rust to get hands-on experience? There's this article called Projects Every Programmer Should Do or something like this. Coding projects every programmer. Yeah. Try this one. Challenging projects every programmer should try. I haven't, so for the record, I haven't done like any of these. Other than the operating system, I haven't done any of these. But if you're looking for some projects, then that could be a good start. Okay. All right, guys, I need to lock in a little bit here, so I'm gonna, don't mind me if I just do that for a second. So we're redoing this and push the context directly on the stack. And so sorry, register state. So we need to make sure this aligns up. But I think basically we're just gonna push. Actually, we need to push in reverse order, I think. So I'm just going to push R15. 10, 9, 8. RBP, RSI, RDI, good. It knows what I want to do. RBX, racks, cool. So then this, we're not doing this anymore. Then we push FQ. Nice. And then actually, no, I did this. I'm doing this in the wrong order. It's push FQ comes first. Because remember the struct layout. RIP is sort of implicitly at the top of the stack. Then we have R flags, then 15 all the way down to racks. And that's kind of it. And then, so now we have successfully, after this code just ran, and we just elegantly pushed all the stuff into this location. And now what we need to do is we need to save the pointer, save the current stack pointer. I mean, actually, for the record, technically, we only need to push call the saved regs. We need to take that stack pointer and save it into the task, and then hit the scheduler. So How do I want to, what's the best way to do this? I think probably the best way to do this is we can then pass this pointer, right? We can pass the stack pointer back into the bridge where we can set it there, I think. What's up, Ahmed? So you push everything to stack and then pop to save or store the context. Yes, that's the idea here. That's not how I originally did it, but like originally I was storing things in the object, but Jakub gave this comment suggesting to do more of a push and pop implementation, which I think makes sense. And so I just want to double check though. RDI, RSI. Yeah. Yeah, RDI and RSI. Cool. So that's the idea. And so now we go over here to the bridge, and the bridge it's going to take a pointer to a task register state. And it needs to save that into the current task. Yes, something like this. I'm wondering. Okay, so let's go ahead and update function declaration. So the bridge, yeah, the bridge needs to have this thing. So Lion Shaft, definitely not the second best program. Who was the first? Definitely not. Definitely not. I'm just a person. Just a person doing some coding that feels fun to me. I think that's the idea. So that's how we're doing things right now. So just to recap what's happened. And so we've been working on this part of the flow. A function, the task is running some kind of stuff. It does a yield. So yield. Oh, okay, that's not what I want. It's good. It does task yield, right? Task yield. What are we calling it here? Task yield doesn't do a lot. It pretty much, I mean, technically we don't even need this anymore. It just calls this preserve task thing. It calls into it. And so the call is going to push the PC. And then now we just jump straight into this code where we just push a bunch of stuff. And so we're pushing all these, like all registers, and crafting our state struct. And then what we want to do is we want to make sure that the task has this pointer and it gets appropriately set over here. And rather than trying to do that from C++, or from assembly, it's much easier just to take that stack pointer value and pass it back into C++ where it can set it in the object. Yo, Ray, what is up? Nice to see you. Back to the grind, bro, for sure. Yo, what's up, Prashant? Do you use Claude Code or other AI for coding? Yes, I do. Yes, sometimes. I try to avoid it. I try to only use it in the right way, in the right situations where it's just helping me do things mechanically, but it's not replacing my understanding. I'm gonna get my hoodie again. All right. So we just take the stack pointer data, we pass it to the bridge. The bridge gets a pointer to the kernel, and then also pointer to this register state on stack, we'll call it, to be very verbose. And then we just make sure to set that in the current task to kind of complete the save process. And then from that point we hit the scheduler and go into the yield impl. So that's cool. So we've done this thing, we've done this thing, we've done this thing, and these are the two things that are left. ASM for restore and switch to task. Let's go into the ASM for restore. Okay, so let's talk as a restore a task and jump back into it. So and so this is probably the best part of today's stream. One of the entire motivations of this cleanup that I'm doing right now, or this re-architecting, is to simplify this exact routine, this exact assembly routine. And so so if you're watching right now, you'll be able to see in real time as I simplify this code pretty dramatically, I think. But so what's the deal? So I'm thinking it makes sense for this to receive a pointer to the register state on stack, to be clear. And then what we're going to do is, the first thing we're going to do is we're going to reset the stack pointer to point there. And so I think that's wrong. Wait, did I get it wrong? I think I got it wrong. We are trying to move, we're trying to reset the stack pointer to be pointed at this argument we received. And so we're going to copy that. So I'm also going to snooze the inline suggestions for 5 minutes so I can have the satisfaction of doing this myself or whatever. So the first thing we're going to do is we're going to set the stack pointer. We're going to set the stack pointer to point to right here at the very bottom of this thing. And we're basically going to do the opposite of what we saw here. Well, it's the opposite of what we did in the assembly up here, but I'm gonna write it right now by just looking at the struct definition. And so, so we need to start popping. That's the deal. We need to be popping from here all the way down. And so it's gonna be pop racks. Okay, here's the part where I'm gonna re-enable the cancel snooze, because I actually want it. Just I wanted to. Okay, 20-second break. Be right back. Okay, so pop RBX, right? We're just going all the way down this list, popping basically everything. RSI, RDI, RBP, R8, R9, 10, 11, 12, 13, 14, 15. Okay, so it's going to be pop R15, and then it's going to be pop the flags. However we do this, I think it's going to be pop FQ. So that's what we expect to see. Pop FQ. And then that's pretty much it. It's going to be the ret. And as a detail, we need the STI. You know, I don't. I like to just keep it around just for reference. But yeah, that's it. And so with our new implementation that is very stack based, this is what it looks like now. Move, pop, 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 FQ, STI, ret. That's it. As opposed to like this, you know, move RDI this from this index, like moving all these things from these indices into registers, doing all this like push pop, like push blah 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 blah. Restoring this thing at the very end because otherwise it's in use. Like all that stuff goes away with our new stack-based implementation. So that's the idea. That is one of the primary reasons to do it like this, for that simplification right here. And I think the question is it worth it? There is a certain simplicity to just simply storing the state in the task that was kind of nice. We exchange it for a little bit of complexity here, but honestly, it's not the worst amount of complexity, and honestly, this code doesn't change very much. So I could see an argument for actually just doing it the old way, because we traded a little bit of complexity. We reduced complexity over here in this assembly routine, but then we increased complexity in the constructor slightly. Because now we need to like do all this sort of like setup of the stack. So yeah, I don't know. I think Yeah, I think I'm leaning towards just doing it like this. I do like the simplicity of the pops and stuff like this. I guess that's worth it. This, it does clean up this code. This code wasn't awfully complex, but it was a little bit fiddly. So maybe it's a little bit nicer just to have this much more kind of stupid code. So yeah, I guess we'll go with that for now. I think my interesting takeaway here is just the fact that there's a bit of a complexity trade-off. It wasn't as much of a slam dunk as I thought it was. I mean, it wasn't as much of a slam dunk as also I think Jakob was thinking because yeah, now we need to do a bit of special stack preparation when we construct a task, which was it's like a slightly cumbersome. So anyway, that's exciting. So I think this is well on the way to working, and we're pretty close to running a test. And so we just did the restore assembly. So now we just need to do switch to task. Yeah. What's up, George? Why is your choice not C? It's a very simple answer. I am much more comfortable with C++ than I am with C programming. So Vakar, VS Code, using VS Code. So Rudy, hey, I'm new to the channel. Just wondering, can it run Doom? Unfortunately, no, not right now. Still in the very early stages of my OS in the grand scheme of things. So I'm focusing on the really absolute core fundamentals of the OS currently. All right. Okay, so yeah, so let's do the last part. So the last part is working on the dang. Sorry. I completely forgot. All my shortcuts as oh my gosh, wow. Holy crap. Restore task. So now we're here in switch to task. And this is the final thing. Yo, what's up, Hack M11? What's up? New to the channel. Popped in the recommendation. Welcome. Yeah, thanks for popping in. Thanks for joining. Okay, so here's what we need to do. And so you know what, actually I think this was okay. So I think so what I opted to do is keep it like this actually. Right, so we're passing in the pointer to the register state on the stack. Into this thing. And it's going to just completely take over from this point. It's going to I think the commenting is a little bit weird. I think my syntax highlighting is a bit wrong, but yeah, it's just going to completely take over. It's gonna forcibly move the stack pointer to this place on the new task stack, and it's going to unload the context. It's going to unload the context and return back into the task. So, and then the question is, what's then this line is kind of interesting. Let's talk about this line. So this part of the code is implementing deferred cleanup. The idea is that when we have a task, it's running, it has a stack, it's running on the stack, and it's time for the task to exit. So it calls task exit and then enters the scheduler, but we are still on the stack of that task. And so it's not clean, it's not sound to free that stack while we're still running on it. That's the problem. We want to release, we're exiting the task, we want to destroy the resources, we want to clean everything up, but we can't do that because we're actually still on the stack. And so to solve this, we implement a deferred cleanup solution where we wait until the next task has been selected and there is kind of a safe place to just to clean up everything related to the old task. And in order to do that, we need to switch stacks. And so, we have the old task. It is exiting. It runs the scheduler to select a new task. And as soon as we have the new task, we can switch stacks onto the new tasks stack and then be in a comfortable, safe place to destroy everything. And so that's what we're seeing here. And so, yeah, we're in the switch to task. And so we have a new task and we also have a pointer to the exited task to destroy. And then if we have something to do a deferred cleanup, we want to swap the stack. And this is kind of interesting. I'm a little bit unsure, but I think it might just be this. So in this case, actually, it's kind of interesting because we're talking about right here. There's this frozen task that has its register state all right here. And we want to switch our stack pointer to point right here, right below this context, and then run a bunch of arbitrary code, actually. We need to be very careful to not clobber this, but it's not really a problem. We just point RSP right at this line, and then we can do more function calls. So we can do this function called destroy task, which under this function called destroy task, which destroys the task. It gets the task to be cleaned up. It gets an iterator to it. It erases it from the container, which runs the destructors, and does all that. And so that's all running in this zone right here. All that cleanup logic is running in this zone underneath, and then that is going to return back to the same location. And the stack pointer is going to be right here. And then that is going to, I guess not that it really matters because we're explicitly passing this thing in, but then we're in a safe place to restore into the task. What's up, Tiago's? Respect no vibe coding. Not today. Sometimes. No, I try to avoid generating a lot of code with pure vibes. Let's take a look at this squiggly line. I'm just gonna comment all this out. I think that's just unused dead code from a long time ago. All right, so do we compile? First try, compile them first try. Let's just take a look at the diff before we even run it. So we got, I mean, the diff is kind of messy, but because I have all these commented lines, but we swap out the object layout. We're no longer storing the state, but we're storing a pointer to it on the stack. We write the register state into memory and then set this thing to point to it. We subtly tweak the struct layout of the task register state. We don't need the RSP anymore because that's actually captured in this register state on stack. I'm going to be, I sort of like being very clear about things. And so I'm going to rename it to register state at stack bottom. I'm going to be super explicit about that. Register state at the bottom of the stack. Hopefully that's understandable. All right. Hello Code. What is up, Hello Code? Got some OGs in the chat today. How you doing, Hello Code? Right. So yeah, tweaking that setup. Then we're just tweaking our bridge. Then maybe just jumping to the assembly. So we got our assembly changed. We're no longer storing things into this region of memory. We are just using the stack for everything. So we, yeah, to adhere to the layout, we push the FQ at the very end, followed by 15 down to racks. RIP is already on the stack. I think that's worth a comment. Now, complete rest of the context. Yep. All right. Yeah. So we got to push Q and then RIP R5 R15 down to racks. That's looking good. Then we get the pointer to the kernel and then get this current stack pointer. And pass that in here. Sounds clean to me. Then we jump to the bridge, and now we have this change where we receive that argument and I actually want to even see it. So that compiled. Let's take a look at Binary Ninja. Let's take a look at the ASM to CPP bridge. And we should see RSI. Here we go, RSI. RSI gets stored onto the stack for some reason, and then loaded back out as racks. Stored back on the stack. I believe here, RCX racks is the pointer. Wait, no. RDI is the pointer to the kernel. Why am I so confused about this? Oh, wait, because, oh, I see. Racks is the return value from this function. So this returns the pointer to the task, and then we're writing into offset hex 10. Which, does that make sense? So this is 8, and I don't know, maybe this is 8 too, so that's plausible that this is offset hex 10 into the struct. Also have Druba. I'm building my own kernel. Yeah, there's no Linux kernel at all going on here. Yeah, okay, so just kind of confirming what that looks like. That's cool. All right, I'm gonna kill the palm tree because we're getting down to the end of time. So Crafty, what name your OS? My OS is not named right now because it's not ready to have a name, I think. I think it doesn't deserve a name yet, but at some point it will deserve a name, and I'll name it then. Okay, so anything else to look at before we run it? Push, pass over here. Then on the other end, so here's the yield. All we change is we don't need to assert the current task or pass in a state. We just call this thing straight up like that, and it uses the stack like we saw up here. It just starts pushing things onto the stack. Yeah, custom kernel, exactly. Zig is greater than Rust for anyone asking. Got some flame war material. Yeah, I'm just using C++ because I know it very well, and I don't know Rust at all. But my recommendation would be to learn Rust if you're starting from scratch and don't have any prior history. So yeah, that's what that looks like. And then lastly, over here, this is very similar. We're passing in a pointer into the routine, which is a pointer to the register state. And that is mostly it. So let's just run it. Let's just run it up. And moment of truth. We'll see if this works or not. Yeah, I think that worked on the first try. Yeah, to me, that is looking like it worked on the first try. It successfully did all 3 tasks. And ran them to completion. Just for fun, we can go over here and re-enable this code, which causes a bit more of action to happen, where we are really starting to run a bunch of tasks. And it looks to me like that's working. So I think that's pretty good confirmation that I haven't completely busted the entire thing. So yeah. Yeah, I would appreciate some hearts in the chat, some dubs in the chat, please. That would be sick. Yeah. So we got our thing working, and so this was all based off of that design critique that I got on Instagram, and we have implemented it, and it seems to have some merit. Seems nice how it simplifies the assembly a little bit. It does kind of complicate the object layout, or stuff like that. Like I'm not the biggest fan of how it adds this pointer over here, because now it's like hopefully this pointer is not null. This pointer should never be null. Like, this is just sort of like the stupid way to do it. I feel like you just put the thing in the task struct. This is a little bit more complicated, but yeah. So this is working pretty nicely. Works. Context. Okay. So Macrae 8. Why am I not using smart pointers? I am using smart pointers when appropriate. But if you're asking about right here, the reason it's not a smart pointer is because this is not it's not really owning a resource. So it's just an observer pointer, and so in that case, it makes sense for it to be a raw pointer. Yep. I have one other idea I want to try, actually. So there's not a ton of time left, but so one interesting thing is, from what I understand, this pointer with the register state thing is only relevant when the scheduler state is like runnable, not runnable. It's not relevant in this state, so yeah, when it's running, there's just no notion of this context thing. I wonder if we can express that somehow. So like you might use a Rust enum, you might use a C++ variant, maybe for this kind of thing. I'm not sure if it creates more problems than it helps with, but I'm curious. And so let's just take a look at the scheduler. So state. So here's an example. Exited. What about yield? Task yield. That's actually in yield impl, I think. So in yield impl, if we have a current task, we assert that it is a running state, and then we set it to be runable. So I've got some questions. Book called Computer Architecture and Design. Haven't looked at it yet. I'm learning linear algebra. Wondering if I could use my basic programming knowledge, specifically Rust, to do systems programming alongside that book. Sure. Yeah, totally. Go for it. So, what's up, Benzene? How's your vacation? Good, thank you for asking. It was great. Nice to take some time off to recharge a little bit. You are late. Unfortunately, you are so late that it's almost the end of the stream. Because I usually stream for about 2 hours, so yeah. Funk channel extremely late again. Let's take a look. So the idea is, what if we could sort of more precisely express like what state is relevant when? Runnable, not runnable. Currently, we're using runnable, running. Not runnable is used, I see. Kind of interesting. Just defaulted to not runnable. Are you going to push this to GitHub? Maybe. Maybe eventually. I'm not really in a rush to do that personally. From Benzi, I checked Discord, you're done with Stack. Good question. So what we did was work on some, like, using the stack to store the context switch state, the register state. User space is not really relevant right now. I mean, I don't even have a user space at all. So not really thinking too much about that just yet. The funk channel. I'm just a small kid trying to learn code. I'm 10. Please don't bully me for some really obscure reason. Yeah, definitely don't bully the funk channel. Please don't do that. All right. Do I have a job? Yeah, I have a job. I work in the music industry. I work in the music technology industry. I'm going to try something kind of weird. And I actually just even wonder if this is even possible. So do I even have variant available to me? I'm just going to try a weird experiment. Struct A. Struct B. Using my variant. Okay. Does this compile? Okay. That seems to work. Let's try this out. So, the task sketch state. Let's hit runnable, running. Yeah, it knows what to do. It knows what to do. Okay, so, and then the idea is that in certain yeah, that's the idea. And in certain cases, like in the runnable case and even in the not runnable case, so I'm compiling with GCC or MSVC. I'm using Clang actually. So so in the runnable case and yeah. I sort of don't remember what's up with the not runnable case. It seems to be the default here, but I don't think that is actually used because clients pass in a scheduler state. So and we only have a couple clients. I guess the IntelliSense doesn't find it, but in both cases here, we pass it. The idle task is runnable, and this is exited, and then over here we pass in runnable for the create task. And so I think this this thing is like sort of unused. I think I'm not going to add this. And so the main idea is that we're going to associate this pointer specifically with the runnable state. Are you sure you're 10? Yeah, I don't know a lot of 10-year-olds that can talk about ABI mismatch. There's a thing called Google. All right, I sense a bit of snark in that comment, and I don't love it, to be honest. Let's not be so snarky with each other. All right, so we're prototyping our new way of having the tasks state. And let's try this out. And so, so I'm going to do it like this. I'm going to put this thing right after. I'm going to okay, do this. And then now the idea is we're going to go through the scheduler. Okay, I already am spotting one thing I want to do. So we're going to default this to null pointer. And so for example, something like this. And I actually sort of wonder what. I might just add sched to the start of all these. Yeah. Is it necessary to strengthen mathematical foundations? I would say no. And so I would agree with apnobenzene. Yeah. Yeah, feel free to join the Discord if you want to chat. But I think, yeah, linear algebra is useful in certain domains, but kernel programming is not one of those domains. Graphics programming, I think, from what I understand, if you're doing DSP, that involves math, but a lot of systems programming does not involve significant math. So let's, let's go through here. So that's sort of the idea. It is no. So we're doing a custom kernel. So no, it's not Linux based func channel. It's a custom kernel. So over here, then it's kind of interesting. There's two things I want to do. It's like one, I want to assert the current state, and then I also want to reset the state. And so how would I do that? And so I guess I could do that's not really what I want to do. I want to do stood holds alternative. And I think this thing is picking up what I'm putting down. And so to be clear, what I'm just doing is I have my existing way of managing the state of the task, but it's actually done in a very C style way. And one of my primary goals with MyOS is to try using modern C++. And so in parallel, alongside, I'm prototyping what it would look like to use a different implementation. How much does the OS weigh? That's a funny question. Good question. It's not too heavy. It's pretty lightweight, I would say. I think it's probably hundreds of lines. It's probably less than 1,000 lines of code at this point. It's not big. Okay, so, and then now, yeah, it sort of already knows. This is interesting. Is that right? So now the idea is to move it into a runnable state. And I don't actually think that's right. So when we have a running task and we're moving it into a runnable state, the point of that, but we're in yield impl. Wait a sec, no. I don't think this is right. So it's like, yeah. We make it runnable. Let me think about that actually, wait a sec. So we have a current task. So yield impl runs after .cpp. Here. So we actually want to check this here. So what I was doing is the task yields, it triggers the context save, we go into here and we store this pointer. But the interesting thing is the state is still running technically because we haven't hit here yet. We just save it in this pointer. I wonder if actually what we want to do is current task v get state. But that's not right. It's sked run a bull. I think. So we already move it into the runnable state. We sort of, yeah, it's like not running anymore. And then by the time we get here, there's actually no reason to do either of these things, which is interesting. So we sort of don't. Or alternatively, and I think I like this a little bit better, we don't do this here. What we can do is we can just simply pass the data. The idea with this bridge thing is to be very, very small. So I don't love the idea of doing a lot of logic and stuff here, actually. So, yeah, the idle task runs when no other task is found. Here's what I want to do, actually. I want to... This starts to complicate the type signature a bit more than I want, but whatever. What I'm going to do, I'm going to make this actually not automatic. So there's only a couple, so there's this thing. So formerly it was like this, right? So what I'm going to do, I'm going to introduce a new thing. That's the task register state. Register state to save, maybe. And our bridge is not going to be responsible for this logic. It's just going to forward data, which is more of the design that I want. And then this code is going to go into here. So M policy, so after benzene, M policy, so I currently only have round robin, but the design, it's designed to support other schedulers if I want to add more later. And so the point of the M policy is to decouple the core scheduler from the policies. What's up, Slay? It's good, it's good. Yeah, we've been doing some cool stuff today. So now we're back over here. If MP current task, right? So now the annoying thing is I have these two arguments now. So now I need to pass null pointer in more places than I really want to right now. But that is okay. It's a little bit weird. Maybe, yeah, there could be room for another layer of wrapper functions that help with this, but it doesn't really matter for the moment. So now over here, I want to assert that task is currently running, and I want to transition it out of that state, basically. Yep. And so now that's what this looks like. And so we're hitting the scheduler now. The old task has been safely, safely kind of saved. And then now we move it into a runnable state, which records this pointer to the register state. Register state, add stack, bottom. The current task register state, to be clear. And then that helps this line read a little bit more nicely. MP current task register state. On stack, to be clear. I don't know. Very verbose. Subgester, yeah, custom kernel. It's, I mean, the OS right now is it's sort of seeming to be like a real-time OS. So it's not really meant to be a general purpose desktop OS. So yeah, not really meant for like users per se. more, I'm thinking more like embedded devices, that kind of stuff. Maybe even microcontrollers, chips, stuff like this. Bishu, what's up? Do you have a job? Yeah, I work as an engineer in the music technology industry. Okay, so let's keep it moving and keep searching for places to update. And so now the idea is uTask dot there. We just do this, the v sched state. Now we're in the running state. And then it's kind of similarly, we go into the exited state. What's up, Slay? Where did you first start to learn C++? I was learning it. I mean, I was learning it in university, but that was a while ago, and we were learning very outdated C++. I think I got my real experience in my first job out of college, where I had a little bit of an opportunity to learn more about some modern C++ and do some training there. All right, what? Is that it? Yeah. Okay, so our scheduler, of course. Oh man, sorry, that's my, you can hear that? That's me shaking my desk a little bit. Or is it music? Yo, thank you, Jester. All the best. Thank you, Slay. Thank you. Yo, let's check this out. So that's the kind of unfortunate part, is that this is how it used to look. You can just simply do these comparisons against a enum, and it looks really nice. And with C++, it looks awful. With the way this function is named, holes alternative, it looks absolutely awful. It's alternative, and it takes a reference to variant. So yeah, not gonna lie, that sort of sucks. I very much prefer the way this looks, but this is, I just wonder if there's a better way to clean that up. I could have a wrapper function, for example, also. You could imagine something that's like variant is, something like that. Or variant holds. Or does variant hold or something. If variant is, or is variant, or is alternative. Alternative is such a cumbersome word. Is variant. Something like that. But yeah, for the moment, I'm just gonna stick with standard C++. So let's check it out. Any other users to be aware of? Not really. I think for every use case I've covered it. So yeah. What's up, Abdullah? What the next with wrap line doing? Policy. That is, so this is a helper function that takes care of wrapping around in the container of tasks, because we're like searching through this task container to look for a runnable task, but we're possibly starting from the middle, and we want to loop through the whole thing though, so we need to wrap around. If we hit the end, we want to wrap around to the start, and that's just what that thing helps with. What's up, Mahir? Yeah, using C++, I'm making kind of like a real-time OS, small embedded OS, basically. Yeah, maybe like microcontrollers. I mean, it targets x86, which is not really a microcontroller architecture, but in spirit, the way I'm designing it right now, it's sort of done in the real-time OS style. All right, so question, are we building? Cool. And we could, yeah, I think we could even try to get rid of these two things now. Oh, but then this is interesting. What is the state? Hold up. Sketch state. So on initialization though, it's kind of interesting. Trace the task with an index. Kind of, it's like this, it's an iterator in C++. It's sort of like this pointer that goes around. Well, it's not really a pointer, but iterator really is the term. And it iterates around the list. Hold up. Wait. An error. Do tell. Func channel with the code review. With the code review, thanks. The question is, what's up with here? And so it's kind of interesting because spy a cat. Word. You can pass in a register. You can pass in a sketch state. But we are always setting this thing. It sort of feels to me like it should always be runnable. So it's sort of interesting because in order to have this thing, that implies that the state must be sched runnable actually. And it's interesting because this new design clarifies this. That wasn't very clear with the old way of doing the ad hoc enum, and then this pointer that really only applies to one of the states. Now it sort of clarifies that relationship when we do it with this way where this thing is only relevant. So that sort of means that yeah. So like when we get rid of this thing, then we need to store this somewhere, and it sort of depends on this thing. doesn't really make sense to construct a task that's not runnable. That's interesting, actually. Is there any... is this the line? There we go. So runnable. When we create things, they are always runnable. That's just how it works right now. And so that we could actually just remove this argument and just hard code it to be runnable. That could be an option, I think, for the sake of not screwing over like all of the code and for the sake of keeping it compiling. What I'm just going to do is I'm just going to assert get state. Assert it is state runnable. Okay, there we go. And then we can, then we can do vis get state. I mean, yeah, this is sort of weird. So we're going to get rid of this. The idea is to get rid of this thing entirely. Oh, so now this is interesting. So here we set the state to running, but we still need to use these two things. So I think what I need to do is we got a new task, right? Which is in a runnable state. Assert new task is runnable. There we go. Right. This is just so unbelievably ugly. All right, so this thing, we're going to set this thing. We're going to assert this is, we're going to register state on stack. Then yes, this changes over here. Register state on stack. Register state on stack. Okay. And then just before we do like anything crazy, then after we have captured this pointer, then we are free to reset the state. And officially make it running. New task register state on stack. Let's compile. All right, peace out, Funk. See you in week 121. Yeah, that dude is smart. Oh, got extra time. Yeah. Yeah, very smart for a 10-year-old. All right, so holds alternative. Yeah, so got this thing. We assert that it's runnable. Get this thing, and then we're free to reset the state later. So a couple. Right, okay, that's looking good. And then we just can get rid of I might even jump to the AI to help me with this. Okay, I'm gonna stage a few things here. Okay. I'm ready to try porting over completely to the variant way of managing the state. Please comment out all uses of the sketch state member throughout the code. I'm going to use Sonnet 4.6. Yeah, so basically now I'm ready to completely move over to the vsked state. So So I just asked it to comment things out. So just try running the kernel. It seems to be working. I think that's working. Yeah, we are completely using this new way of modeling the state for the task. And it's either a smart idea or it's pretty stupid. Yeah, you just see we commented out of the struct. We commented out of the constructor. We commented out of all the constructions. Comment out any of these assertions. And now we're just all about this vsked state. Seems kind of cool to me. Seems like it works. I think just the question I'm hung up on is like this question. So maybe I can allow, maybe it's nice to allow constructing a task into like random states. But because of the way we've modeled it, this place to store this pointer is only available in this state. So as a consequence, if you construct it with like a weird state, there's nowhere to store this register state, and so you just can never run that task. Like the code will set up the stack. It just will have nowhere to store that that state. So I don't know. All right, I'm feeling pretty good though. Like that was a very interesting experiment. Just gonna check the chat. It's not based on anything. 7th Sheep is a custom kernel. Building it for Intel. JKing, it's for targets x86. Thank you, Apnobenzene. Sorry, I didn't quite understand this. Thank you, Hamza. All right, y'all. I'm going to call it quits for today. It was a good stream. Thanks, everyone, for joining. I'm going to be back at it next week, but feel free to join the Discord if you want to chat some more. And I think I just want to say, please subscribe. Yeah, I got to plug myself. Please subscribe to my channel. If you are enjoying this content, I would really, really, really appreciate if you just give me a subscribe. That really helps me know that people are resonating with the content I'm making, and helps you stay notified when I do streams, which is every week on Sunday. So I wish you a great week, everyone. Have a nice one, and I'll see you next time. Peace.